Imagine the very last flash of light in the cosmos, a solitary explosion tearing through an empty void, followed by an eternity of perfect darkness. Before that final spark occurs, the universe will have waited in the dark for a length of time that defies human language. To understand our future, we have to look at the present. At 13.8 billion years old, our universe feels ancient, but on a cosmic timeline, it is still in its infancy. We are living in the Stelliferous era, a brief window where galaxies are filled with the light of actively burning stars. But most stars do not have the mass for a violent end. Roughly 97% of them, including our Sun, will eventually shed their outer layers and leave behind an incredibly dense Earth-sized core. We call this a white dwarf. These objects are a documented reality. In the early 20th century, astronomers like Williamina Fleming identified their unique spectral signatures, proving that these blazing hot stellar remnants were scattered throughout our galaxy. Thermodynamics dictates that because a white dwarf has no new fuel, it must eventually radiate its remaining heat and become a dark, invisible black dwarf. Yet in our 13.8 billion-year-old universe, not a single one has been found. The cooling process simply takes longer than the universe has existed. A white dwarf is a dead star. Nuclear fusion has completely stopped, meaning the core has no internal fire and no way to generate new energy. It glows only because of the residual heat left over from its former life. Gravity still pulls inward with massive force, but the star avoids collapse through a quantum mechanical effect known as electron degeneracy pressure. The electrons are packed so tightly that the laws of physics prevent them from being squeezed any further. The text shown here explains the physics of degenerate matter, specifically the Pauli exclusion principle. This principle dictates that no two electrons can occupy the exact same quantum state, creating a rigid pressure that holds the dead star intact. This quantum pressure has a mathematical ceiling. In the 1930s, Supermanyanan Chandrasekhar calculated that if a white dwarf reaches approximately 1.4 times the mass of the Sun, gravity will finally break through this electron shield, causing a total collapse. If the star stays below that mass limit, it becomes trapped. It cannot generate heat, but it is physically barred from collapsing. Its only path forward is to slowly bleed its remaining thermal energy into the vacuum of space. This chart shows the white dwarf's decelerating cooling curve. It drops steeply initially, but radiation slows drastically as temperature falls. Internal crystallization releases latent heat, re-warming the core. Finally, a thin insulating atmosphere traps this heat, pushing the black dwarf state into mathematical extremes. These roadblocks stretch the timeline from billions of years into trillions and eventually quadrillions. Long after the last burning stars have gone out, the universe will enter the degenerate era, populated by these slowly dimming remnants. Eventually, the star reaches thermal equilibrium with the cosmic background. It stops emitting net radiation and becomes a black dwarf, a dark, freezing, Earth-sized sphere of diamond-like matter. Imagine the universe 10 to the 1100th power years from now. Galaxies have dissolved, and the Stelliferous era is long over. The cosmos is a graveyard of invisible black dwarfs drifting in total darkness. While these frozen corpses appear stable, quantum mechanics allows for a microscopic loophole, quantum tunneling. Over an incomprehensible stretch of time, quantum tunneling allows atomic nuclei to bypass their repulsive barriers and fuse. Despite having zero thermal energy, the carbon and oxygen atoms inside the black dwarf slowly transmute into iron. This accumulation of iron fundamentally changes the core. As the composition shifts, the star's Chandrasekhar limit, the maximum mass its electrons can support, steadily begins to lower. The black dwarf is slowly sabotaging itself. The same quantum rules that kept it stable for eons are now undermining the very pressure that prevents its collapse. Eventually, the iron core causes the black dwarf's mass to exceed its newly lowered Chandrasekhar limit. Gravity finally wins. The star collapses inward in an instant and detonates, tearing through the darkness in a massive supernova. This will be the absolute last astrophysical event to ever occur. It is the final act of creation and destruction in our universe. When the explosion fades, the universe will enter a state of permanent, irreversible silence. No more stars will form, and no more light will be generated. The universe will end with these solitary sparks across the void. We exist in a privileged moment, alive in the brief, luminous dawn of cosmic history.